today we're continuing with the central force problems, and actually we're doing the Kepler problem. Before that, however, let's take care of a sign problem from last time that although it was incorrect when, the result was correct, somehow mumbo jumbo from my part, but if we're doing correctly, the result is the same as the one last time. So here, when I use the rotation angles, and then I solved this equation, this one, I solved it for this term, right? So basically this term, appeared on the left, but it was on the right. And then I was supposed to move this guy right on the other side, right? So here it is with a minus, okay? And then the x2 dots is with plus, all right? But also here I said that this r was written like r, or rotation of theta minus pi on 2, but in truth is r is a rotation of pi on 2 minus theta. And then if we do the calculation properly, the result, as I said, is correct. So the equations at the end are correct, okay? And well, if you're still around next year, you can take a course with me in mathematics applied in classical physics. Let's just put it like this, okay? Where you will see that actually the pain of changing variables barehanded like this is unnecessary, because there is a theory from Lagrange and Hamilton, like for 200 years ago or 150 years ago, in which, we can do these changes of variables very easily in one line and then just write the equations of motion, right? So it's called Lagrangian and Hamilton, Lagrangian mechanics. That's where it's extremely easy to do the changes of variables. Whereas like this, it's a pain. And I was telling you last time that one has to pass through this pain at least once to appreciate the value and the beauty of the coordinate independent formulation of classical mechanics. But that's my plan for next year anyhow. So that's that here. Okay, so now we're moving forward to the Kepler problem. However, before that, I wrote down in a more compacted way and clear way what we did last time, so you have it done, like, okay, so you know where you are and what's going on. So central force problems are concern the motion of a mass point, so it's a point that has weight, if you want, under the attraction or under the influence, attractive of repulsive, doesn't, there is no difference in it, at least at this level, of a source. If it's a gravitational force, it will attract following the law of gravitation of Newton. Could be something more fancy, something, that has other kind of functions, modeling the attraction or the repulsive. For instance, in molecular mechanics, they use a potential that is of the form, so I always know the potentials. V of R is something like A over R at 12 minus B over R at 6. It's called the Leonard-Jones potential. Okay, just because we're here, just to give you an example that there exist other potentials. And they use it in molecular mechanics as a simplification, right? For determining the equilibria of molecules. So they say, oh, molecules are forms of atoms and they attract each other by this law. And it works good enough, although people know that that's not classical mechanics that models molecular dynamics, right? You need quantum mechanics, right? But for computational reasons, they kind of simplify things and they use this kind of approximation. So this is just to give you an example of other potential. So we're looking at this class of problems in general, right? So they are, they lead to a second order ODE that looks like this one, right? And then we specify this, so V being the potential, then its derivative is minus the force field. So there you go. the derivative it is minus the force field, right? The force field being, you know, the right-hand side of the ODEs, right? The ODE second order. Okay, so and then last time we basically massaged this thing, right? You know, we played with it. So what did we determine? We determined that these kind of problems conserve energy. So there is this quantity that is formed by the kinetic energy plus the potential energy, and this is conserved along the motion, meaning that it gives you a value, right? It's the same value, let's call it, let's say H, right? It's like a number that is the same along a particular solution and is the same with the value of the constant at time zero, right? So the initial conditions are fixing a value of the energy, and that's maintained along that entire solution. It doesn't change. For a different solution, you'll have a different constant of energy, right? But it will still be constant along that solution. So these things, you know, are called conservation of energy, or the integral of energy, right? It depends what denomination you want to use, but that it means the same. Another conservation law that we determined, but we didn't name it, right, is this product R cross V, right? This is actually the angular momentum for a particle of unit mass, okay? So by the way, in this picture, if you want, you can think that, you know, the mass is taken to be 1. Okay. Anyhow, it's irrelevant in this discussion because it can be included in the formula of that force field, right? That force function. Okay, so we saw that this quantity, again, it's constant along any solution, right? And but this, in this case, is a vector constant, right? So because it has 3 components, okay? So it's the same idea. Whatever is this vector constant at time 0 for some initial conditions, it will, along the entire solution, this R cross V will be the same, right? We will have the same value of this constant. So in this class of problems, for sure, we have 2 conservation laws. The energy, which gives us 1 number, is a constant along the thing, but it's 1 number. The energy is represented, it's a scalar. And then a vector constant, which is the angular momentum. Well, you don't have to know that is the angular momentum, it's just a vector constant, which gives us 3 numbers, right? If you want, okay. Anyhow, so then what we did, we took this constant C and we said, well, okay, if it's 0, we prove that then the motion stays on the line, okay? So, you know, because the radius vector and the velocity, they're collinear, so they have to stay on the line all the time. Whereas, you know, if the constant is not 0, then it's a vector constant. We have that the radius vector moves on a path that is always not the path. So the radius vector stays constant, stays perpendicular to this constant, and the same with the velocity vector. So we have something that moves like in the same plane, and this plane is always normal to the constant vector. So the motion is planar, is in the plane that is normal to that constant vector. Cool. So then if is this the case, then we can choose, you know, a particular plane that, you know, we say, okay, we'll be there all the time. So we can choose to be the horizontal plane, whatever, okay. But there is something more into it that we didn't put down last time, okay? So if we remember from calculus, what is the area swept by the radius vector? Okay, so the formula is really a half integral of R cross V. That's from calculus 3. So if this R cross V along a path is constant, then the area covered in the same time interval will be the same, right? So I have to time it. If here I have delta t and here I have delta t, although, you know, the radius vector, you see that it varies, but the area covered in equal times will be equal. So equal areas to equal times. And this is called the area law. And this is a consequence of this conservation of angular momentum. So I know we didn't say this last time, but this is one of the important consequences, or one of the important properties, if you want, of central force motion. Okay, next. Next, we're done with the general problems. And we're saying now, let's focus on gravity. Let's focus on the motion of a satellite, if you want, okay? So for that one, assuming that the Earth is perfectly round, so that if it's perfectly round and it's a gravitational source, there is a theorem done in, we could do it in this course, sometimes it's done in classical physics, where it's proven, we can prove that this perfectly round Earth attracts objects the same way as the entire mass of the Earth would be concentrated in one point. So it's basically the center of the Earth that attracts everything, okay? So it doesn't really matter if the Earth has a radius of 10K or a radius of 10,000 K. If it's round, what matters is its mass. And this mass is like it's concentrated in one point in the center there, okay? So we're going to look at the motion of a satellite, if you want, or whatever, assuming that the Earth is perfectly round. So there you go, the mass is concentrating in the center. And what we're assuming, we're also assuming that there is no solar wind, there is no dissipation, so there is no atmosphere of the Earth, if you want, right? So the atmosphere will slow down the motion, there will be some friction with the air, right? So we're in a kind of an ideal setting. And of course, you know, this would be another assumption that the mass of the satellite does not affect in any way the motion of the Earth. And I think we can be pretty sure that that's the case, okay? That's one assumption that we can say, well, it's quite true, okay? It's quite true. I don't see how a satellite of 2 kilograms would affect in concretely, you know, the trajectory of the Earth, right? Yeah. Okay, so from Newton, and not only Newton, we know that in this case, the potential has the form minus mu over r, whereas mu, right, in this exercise, right, we take it as g gravitational constant times the mass of the Earth, let's say, okay? But the same modeling applies to motion of Earth around the sun, if you want, ignoring the other planets. So again, we're ignoring the other planets, we're ignoring everything, right? There's just nothing else exists, nothing else exists, that the sun as a mass point, gravitational source, and the Earth as a tiny little body, right? I mean, the difference of mass in between the Earth and the sun is huge. It's so huge that actually the center of mass of the system is inside the sun. The center of the mass of the solar system. So you put together Venus, whatever, you know, Mercury, Venus, Earth, Mars, Jupiter, all of them, put them in a bucket. And then compare it to the sun. The center of the mass is inside the sun, right? So I said this to the other students too, you know. So it's interesting, yeah. Okay, so we're here. So from now on, we're continuing with that problem, right? That we had to do, and we're going to determine slowly what is going on with this motion, okay? We analyze everything slowly, right? So what was, I forgot how was worded the first part, just bear with me. Wow. Okay, so was something like, okay, so we have the energy relation, right? Okay. And we have to study this stuff. Okay, so in general, so let's start now. In general, right? Okay, the motion, the central force, right? Problem in polar coordinates. Okay, is given by, okay, so are those two things, right, that we did last time. So it was, right, so we can write them something like this. R dot is VR, right? And VR dot is R V theta dot squared minus F of R. And I'm going to use interchangeably how I feel. It depends, right? So we have R dot is VR, and V theta, right, is nothing else but a notation for theta dot, right? So they're the same thing. So, you know, it's either we write it as second order or we write it as a first order. So, and then also we had the other one was that R theta dot, see, I'm not putting V theta, plus 2 R dot theta dot is 0. I think this was a square there, right? Let's check. Where is it? Where is it? No, it's R2 dots. I knew that there is something going on there. Okay, wait. Right? Okay. So now we have this f of r to be this guy. So what I'll do, I'll just substitute it in there, right? So we'll have r dot is vr, and vr dot will be rv theta squared. Why did I put a dot here? Because I'm just going. Okay, there you go. All right. And the other one, the other relation, no matter what we do to it, right? So this is because f of r is mu over r squared. This one is actually equivalent to dB dt of r squared theta dot equals 0. Okay, the second relation. Okay, so I'm going to flip the page. Okay, and see where I'm getting slowly, right? So for one thing, we have dB dt of r squared theta dot is 0. So r squared theta dot will be a constant, right? I don't know what this constant is, but in the problem, I said, okay, check out that if you do r cross v equals constant, okay, you're going to end up with something like this. That's how it was in the assignment. So remember, right, so recall that actually r and v, right, are in the XOI plane, right? So we said that without losing generality, we work in the horizontal plane. Okay, we can do that. All right. So now if this is the case, these guys actually are equivalent to something like ijk, right? So this is, I'm writing the vector product, right? And then x, y, z, right? Because r is x, y, z, right? And then I don't want the x. Okay. X dot, y dot, z dot equals that c vector, right? But c, right? C is perpendicular to the horizontal plane, right? So this actually, this c vector is 0, 0, and some little c, right? It's absolute value. Yeah, because it's perpendicular to the horizontal plane, so it has no components there. Okay, and actually, again, you know, it's the same thing with R. So R has no Z component, so these guys actually are not here. So I can just take them out. Yeah. All right, so this, this is equivalent to x if when we do it, right? We'll have that 0, 0, x, y dot minus x dot y equals 0, 0, c. And then this is equivalent with x, right? This kind of stuff equals c. And now, what did we do? We passed to polar coordinates. Okay, so this means that x dot is r dot cos theta minus r theta dot sine theta. We did that already. R dot sine theta plus r theta dot cos theta. So now when we're going to substitute, so I will not do this, but when we're going to, if one sits to do this job, right? So you go and you put it in there, right? All this stuff. What you're going to discover? You're going to discover that this is actually r squared theta dot equals c. Okay. So in effect, this constant here, right, is actually that c. Okay, so that was part of that exercise. Okay, so in the exercise, I was saying, assume that we are, in the x or y plane, right? And then the relation becomes r squared theta dot equals a constant, right? And actually, it was done for f of r in general. Here, it doesn't really matter. Okay. Okay. All right, let's see the energy relation, right? So the energy relation was written in this way. Plus V of R, right? Well, in this case, right, so I'm gonna say here, energy. The energy relation. Okay, so this would be V dot V, that's what it means, the V squared, and then minus mu over R, right? And we know that this is constant along any trajectory, and we can call it H, okay? So now what we're gonna pass, we're gonna go to polar coordinates, okay? So again, I'm gonna say, well, X is R cos theta, y is r sine theta, x dot, y dot, blah, blah, right? And then we have this E of r theta, r dot if you want, and theta dot, there you go, okay? Or VR and V theta. So now I'm gonna substitute these guys, right? So is 1 over 2 the vector v dot the vector v. But what is the vector v, right? So we have to write this in polar, right? So this would be x dot y dot times x dot y dot, right? So that's, okay, so v, right? So where should we put this to make it clear? We are in plane, so we have these things, right? So here, minus mu over r. And now, so this is 1 over 2 x dot squared plus y dot squared minus mu over r. Yeah. So this will be 1 over 2. And now we should take whatever is here, right? This formula and this formula and put it here and square it. Okay. So this is formula 1. Let's say this is formula 2, 1 plus formula 2 squared, okay? You square it, and then you're gonna discover that the result is 1 over 2 r dot squared plus r squared theta dot squared minus mu over r. Okay, so in other words, if you do the calculation, you're gonna discover that the energy in polar coordinates has this formula. And I honestly advise you to do the calculation because you have a final coming. And this is the kind of stuff that I can ask. There is nothing wrong in it, nothing hard. You just do a calculation, right? So this is the energy in polar coordinates. Okay. And by the way, it will be constant along any solution, r of theta, r of t, theta of t, whatever, right? Okay. So let's see what we have. We have two relations. On one hand, the energy conservation. I'm going to ask, how come you know it so well? I know it well. If I know something, I know this, okay? So this is constant, right? So this is a constant, then this h, right? Constant. And then also we have the momentum, if you want. And I'll write it in full blast, right? So this was r squared theta dot, okay? And this is, again, constant, and we called it c. So we have two constants along a trajectory. So along a trajectory, r of t, theta of t, r dot of t, theta dot of t, we have these two constants. So this, wherever it moves, these quantities will be the same, okay, as they are at time zero. That's the thing. So now we start to do it little things, okay? So from this one, we can say, oh, but theta dot can be substituted in this way. And let's do this. It doesn't really matter if c is 0 or not, right? Because I'm not dividing by c. Okay, which means that I can take it now, okay? Here, I'm taking it now, and I'm gonna go with it there. Yeah. So what happens? Then we have that the energy becomes 1 over 2 r dot squared plus r squared, and instead of theta dot, I can put that thing. So I'll have a c squared over r at 4 minus mu over r equals h. Okay, or 1 over 2 r dot squared plus c squared over r at 2 2r at 2 minus mu over r equals h. So what is this? Okay, that's what you have to show, right? So this is happening like this. So along any solution, r of t, r dot of t, theta of t, but we don't need this one in theta, okay? Okay, we have 1 over 2 r dot squared of t plus c squared over 2 r squared of t minus mu over r of t equals h equals what it is 1 over 2 r dot squared of t naught plus c squared over 2r squared of t naught minus mu over r of at t naught. So along any solution, it stays constant. Where what is c? C is r squared at t0, theta dot at t0. Okay, that's what it means. That's what this relation tells me. Okay, so in this relation, there is a constant that is set put, that mu. We don't touch that one. That one is like 5. It just sits there forever, right? But then we have these two guys, the c, the constant of the angular momentum, which can vary because every solution will have a different c, or maybe there are two is the same c. I don't know, but you know, in principle, it can vary, right? And h, right? The energy. Okay. And this is actually, it's the reduced energy relation. Why is called reduced? Well, as you can see, if you compare it with this one, theta dot disappeared. Theta dot became, you know, it's covered by that constant C, but it's not there. It's a constant, right? I'm not that theta is not a constant, but it's in there in that term. Oops, I'm losing my. Okay, good. All right. There. Okay. So it's called reduced because from how many arguments we had here? 1, 2, 3, 4. In this case, we have an E that depends only on R and R dot, isn't it? R and R dot, not R dot. Right? So it's we lost a pair on the, we didn't lose it, we just, okay. All right. And, you know, before moving on, okay, so let's see what I was saying here. Okay, discuss the range of motion in two cases, C0 and C0. The range of motion from where? From this guy, okay? So let's see what it tells us, okay? So we have what? We have that 1 over 2 r dot squared plus c squared over 2 r squared minus mu over r equals h, right? And how did I taught you? Oh, you know, this is always positive. So whatever we're gonna have here, right, is gonna have to have h minus c squared over 2r squared minus mu over r has to be positive, right? So here it is, the range of motion is decided by this inequality, the range of motion of R, right? So it has to be less equal than H. Okay, and actually this quantity here, this guy, it's formed by the potential. So this was the potential. And this term is due to the, what I was saying, you know, to you last time, the rotational forces, if you want, the inertia that pushes things out, right, is a corrected. Okay, just, I won't mess you, okay? So it's just that term that shows up because the system rotates, right? The particle rotates. So we have to put in somehow this thing that, you know, is coming from the centrifuge, right? It goes out. So I could say centrifugal term, something, okay? So together, actually, people call this, this quantity the effective potential. And this is a formula, right, that, okay, let's make it nice. Centrifugal term, right? So this is a function of R. So this is a function of R with C as a parameter. So C is a parameter, meaning it can take, you know, values, and we might have, you know, bifurcations in the looks of this function as C varies, right? Okay, the point is that this inequality will tell us where R is supposed to be. Remember, R is the distance from the satellite to the Earth, to the center of the Earth, okay? So I said, well, first do C equals 0 and plot this thing. So if I'm plotting that inequality, basically what we have a picture, okay, okay, we don't need much. We have a picture that kind of looks like this. So this is V effective of R, right? And this is R. That's how it looks if we put, you know, whatever. So basically this one is minus mu over R, right? Where mu is like 1 or 5, right? So mu is positive and is fixed, right? This is, okay, so if we plot it, it looks like this thing. And remember, R is always positive. So now if I wonder what would happen to my satellite if there is no rotation, because C0 means that there is no rotation. Well, if there's no rotation, it will fall onto the Earth. And this should be obvious. It should come clear from this picture. Let's see, how did we do this? We said we have to take levels of energy that we represent as horizontal lines. So here is an H that is negative. You know, I can take any H that is negative. So what is the range of motion? Where is R allowed to be, right? Remember, we have this inequality. So V effective has to be under H. So if the level is here, right, down here, the allowed interval of motion is here. So it's really close to R equals 0. In other words, my object will have a maximum distance from the center of the Earth, but then it will, you know, it's just this part here. So that's it, you know. If I'm a little bit up with the energy, so I'm here, what's the level of, what is the range of motion? Oh, it will be just this bit. So V, the green curve has to be under that pinky one, right? So here I'll have an R max, but then, you know, I can play only from 0 to R max, right? So this picture tells us really that, you know, I will have R in between 0 and an R max, which will depend on where the level of energy is. And this is if H is negative, right? Whereas if H is greater or equal than 0, there is no motion. And this no motion thingy, you can see it here, because what we're doing here, we're looking for R that solves this inequality, right? And look at this inequality. If H is, oh, sorry, not that is no motion. It can be anywhere, sorry. Bah. Okay, so R is in between 0 and infinity, right? Because, you know, it can be, if H is up, right? It can be from 0 to wherever. Okay. Yeah. So any R in this would solve this inequality. That's what it is. Okay. And moreover, we can actually draw the phase space of this thing, right? We can do the phase space of, now that we're here, why not, huh? So how was it with the phase space? This is R dot, right? And then we have an R max. So for instance, for the purple curve would be something like this. Okay. So how what is the equation of motion, by the way? Right? So we had R dot is VR. VR dot was C squared over R3 minus mu over R squared, right? And now we have C0. So we have R dot is VR. If you want, this is VR is the same thing, right? And VR dot is minus mu over R squared, right? So R dot is increasing where VR is positive. So I'm looking for something like that, right? That's the purple one. If I want to do the blue one, is something like this. Oops, it should come exactly where it is. Something, there you go. Okay, well. Okay. All right. If I take a higher one, right, like a level here, I would have another of these curves going like this. Yeah. So the point is that the thing will fall onto the earth, okay? Which makes perfect sense. Okay. And for H positive, can I represent the motion? I guess I could go like boop. I don't know. I'll just leave it like this. Okay. All right. So now we go to H to C non-zero, right? So that's when we have rotations. So we have rotation. Okay. So what are we doing here? So we have V effective of R is C squared over 2R squared minus mu over R, and we want it less equal than H. Okay. And we're in the case where C is non-zero. Now, if we're plotting this one, let's fix C to be 1 and mu to be 1. It doesn't really matter. The pictures will all look the same. And they would be like this. So this is R, and where is our potential? Will look like this. Okay, so this is V effective of R, right? For some C fixed. Okay, and now we do the same thing with the energy, right? So if the energy is down here, there is no motion, right? And then the motion actually starts at this level, which is the bottom of the potential, right? So this is the point where V prime effective of R is 0. So when we compute it, we will see that this point actually is, so I did, where is it? C squared over mu, okay? Okay. Well, excuse me a second, guys, because I'm not sure what's going on outside. Just two seconds. I have to look, you know, because it's one of these police cars or something. Well, my guess is someone is sick. Okay, so the firefighters are here. Okay, so there you go. So if we compute this, we get that R is C squared over mu. That's the bottom there. And what is this bottom corresponding to? Oh, this is just a fixed point, right? It doesn't move from there. The object will just stay as this distance all the time because there is no green curve under the dashed red one, under this level of energy, right? So, and what is this level? Oh, this will be actually the value of V in its critical point, right? Now we know why we did all this calculus. So let's say HE, you'll see why I call it E in a second, is V effective in C squared over mu. So this HE is actually minus mu squared over C squared. So there you go. And so it's the level of energy where is the bottom of this effective potential. And I was saying for this value of energy, there is only one position allowed, a distance R equals C squared over mu. So that's actually an equilibrium because it doesn't move from there. So it's actually the satellite will move at the same distance around the Earth. So it will be a circular orbit. Okay. That's what it is. And now, so this is for H. So this is H less than HE, which will be minus mu of squared over C squared, whereas this here is H equals HE, right? That's what it is. And now I'm going up with the energy. Okay, let's say we put it a little bit more. Okay, so let's change the color. So let's have a little blue one, okay? So obviously here, well, I shouldn't use obviously. So this is for levels of energy that are in between HE and up to 0, right? Because in 0, something happens, right? You see that in 0, I will go with the line, you know, whatever the green one, you know, will continue to infinity, right? The trace of the potential. Whereas this one, in this case, right, the potential is under only in this interval, right? So I will have some allowed range. I will have an R min and an R max, and these values depend on H, because if H is lower, these guys will shrink in the interval. If H is bigger, it will open the interval more, right? So I'll call them as they depend on H, yeah? So for H in between, so I should do something like this, right? I should start writing what we discovered. For H less than HE, which is minus mu squared over C squared, we have no motion. Then for H equals HE, we'll have R of T equals RE equals C squared over mu. We have circular motion. Then for H in between HE and up to 0, we have R of T will belong to an R min that depends on H, and it goes up to an R max that depends on H. And if I want to represent this, this looks like, so let's say, okay, let me do a picture. So you have here a circle. Oh, okay, I'll try to do 2 circles now, one into another. Okay, so it's something like this, okay? So this would be the R min, and this is the R max, okay? And now how the orbit looks from what we know up to now, okay? It varies in between R min and R max, right? And it's a continuous path. So I would think that it would look something like this. Right? So it's a continuous path in between an R min and an R max, right? It's not an ellipse in any way. It's a rosette-shaped thingy. And this is what we will always get for an attractive force of a central force. Actually, that's the generic picture of this bounded orbit. So up to now, in my mind, what is the satellite doing? Oh, it's going in and out, you know, kind of all the time, you know, like boo, boo, boo. So if I'm looking at this point, that is the furthest point possible, it's called an apogee, I think. I hope I'm right. I think the apogee is the furthest one, right? So this guy will move right from right in time, right? It will be and then nice, huh? Okay, so that's what we get up to now. All right, now I'm going with the energy at 0, right? When we have the energy at level 0, here it is. So this is H equals 0. And then even higher than 0, there is an R min possible that again will depend on H, but then the satellite just runs away. It's going away. So it's unbounded, right? So for this um, h greater equal than 0, we have that r of t is possible to be, right? So it will be in between an r mean of h, but can go to infinity. So if it has enough energy, and where is the energy hidden in this thing? Remember, the energy is this thing, right? So, uh, right? So there's the energy formula, right? So I'm talking about this. So this is a sum of the potential and the velocity there, the square of the velocity. So in other words, if we push this velocity to be really high, right? So you, right, shoot that satellites with really high velocity, it will just go away, which is absolutely physical, intuitively correct, right? And that's what it's telling us, you know, if you have enough energy, you're gonna shoot it away. And that's that, right? That's how that's what it tells us. Hmm? That's what we know. And you know, these kind of pictures of this effective potential, my God, guys, if you know what a long shot is, you know, they use it in chemistry, they use it everywhere, you know, and this is like the first encounter with it is 1D, because you can have these potentials in 2D and 3D, right? And they form these surfaces of whatever motion, and then, you know, you have these balls where, you know, the bounded motion or unbounded, because it matters, right? It matters to know what's going on. Okay, so there's that. Now I was asking you, what is the stability of this point here? Okay, so that's what I was asking, right? So now if we go with this point, this should show up as an equilibrium in the system. So we have r dot is VR, right? VR dot was, what is it? C squared over R3 minus mu over R squared, right? So if we do the equilibrium, you're gonna see that RE and VE, let's say, okay, this would be our friend, what we discovered there, and the velocity is 0. And then if you do the linearization, like I taught you, blah, 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 you're going to discover that this equilibrium is actually a center. So we would call it spectrally or neutrally stable. However, there is a bit in this course that I have to do next week, in which I have to show you how to do stability for this kind of systems. And we will see that actually this is a stable equilibrium because it's inside the ball. It's constrained to be there. It's like a ball that cannot do anything but go down. Okay. But for now, let's just call it that is neutrally stable. Okay. So you'll find, you know, if you do the eigenvalues, whatever. Okay. That's one thing. Then the next part was the integration, right? That was it, I think. Right. Before the integration, I want to still make you attentive about something, okay? So we have, right, so in polar coordinates, okay, the motion of the satellite okay, is given by, okay, so we have r dot is VR, VR dot is, let's just leave it how it was, okay? I'm going back to the initial, before substituting there. So it was r v theta squared minus mu over r squared. And then if we're to do it like at school, right, v theta, and then we ended up with that relation that writing it in v theta and whatever, but I like it like this because in this way we can detect the integrals of motion, right? So when we pass to polar coordinates, this is the system that we obtain, okay? And, you know, as a normal student with no physics background, I'm like, I want to solve this one, man. Okay. So all what I'm showing you here is that, look, we cannot solve it just like that, but we can take advantage of energy and momentum and whatever. And that's why, you know, this stuff is cool. And you can come back and say, but how do I know that the energy is conserved? How do I know that the momentum is conserved? And I will answer you, come and do grad studies with me, and we're going to learn how, because it's always the consequence of asymmetry in the system. Okay. For now, let's just take it as it is. So this one, right, we said, oh, this is equivalent with something like, right, r squared theta dot is a constant, right? So we called it C, which is r squared at t naught if you want theta dot at t naught, okay? And then we went with this thing. So this is nothing else but r squared v theta if you want this C. So we took this one, and from here, we said, okay, v theta is C over r squared, and we substituted into, right, into here, right? Okay, so basically we then obtained this, what I call the reduced system, right? So it was C squared over R3 minus mu over R squared. And somehow, that's what I wanted to get, okay. Say we solve R of t, VR of t somehow, okay? Maybe I can solve it, okay? Then what is theta of t and v theta of t? What are these guys? What are these guys? That's the question I want to answer. Because, okay, we can do reduction, it's called. So we reduce from 4 equations to 2 equations. That's what they are, right? But once we solve this reduced system, how do I go back to the full one? How do I recover the stuff that I kind of reduced it on the way? It's called unreduction, right? It's called reconstruction, actually. So how we do this, we basically take r squared. So remember, r is known, right? So this is something that we know is a function. It's like t at 3 or something, okay? So we take r squared of t, right? Theta, or r squared theta dot, I'm going to write it again in this form, is c, right? Well, this is equivalent with d theta at dt is c over r squared of t. Remember, r is known. So what we get here, we get that d theta is c over r squared of t dt. So what is theta of t? Oh, you know, it will be whatever integral we get from here. So we're going to end up with theta of t. And of course, I don't have room to put it here. I'll just flip it. Cool. Okay, so we are here. D theta is c over r squared of t dt. So I can do boop, boop, right? From theta 0 to some theta, like the physicist, okay? From t0 to t, if you want, right? So we end up with theta of t will be theta 0 plus integral t naught to t of c over r squared. Now I'm a mathematician again, huh? Of u du, where r of t is known from the integration of, let's put 2 stars, which is, where is it? This one, right? 2 stars. Right. So this is hello reduction. And this is such a strong method, you have no idea. Okay. So for nonlinear ODEs, I used some whatever the conservation of angular momentum. I reduce it to 2. And actually now when we're gonna deal with this one, so with this one we can deal in various ways. Now the way I chose it to do it in our course is really to end up with how the trajectory looks, okay? I'm not sure how in a rush are you guys, okay? So now I'm gonna write, you know, Kepler problem classical solution, okay? So I'm gonna take this one and I'm gonna write it as R2 dots plus C squared over R3 minus mu over R equals 0. That was already, that was the point B of problem 4. And I was telling you what to do, right? So, okay, let me check my signs here because they're backwards, right? And somehow, if we do those transformations, we're gonna end up with the formula of R of theta, okay? That's the beauty of it. So, okay, let me show you how it's done. I see that you're still connected, not tired yet, okay? So the first thing I was saying was that, look, use this equation, okay, to write something like dB dt is C over R squared dB d theta. Okay, that's what I put in your assignment. So now if I have to do dr dt, so this is the second derivative of R with respect to time. That's what I have to change in there, the time from t to this theta, okay? So instead of expressing the path, the trajectory of R in time, I will express it in terms of the angle theta, okay? So if this is our R, right? I'm gonna do an R of theta, okay? So I'm gonna see it as an R of theta, okay? That's my logic now. So if we do dr dt, this would be C over R squared dr d theta. Now that was easy, okay? What about the second derivative, right? So here I'm gonna write again this thing. No, it was C, right? C squared minus, okay, where is it, okay? It's backwards again. Okay, so we have dB dt is C over R squared dB d theta. So we ended up with dr dt is C over R squared dB theta. And now I want to do d to R dt2, right? So this is ddt of dr dt. So it's ddt of C squared, no C, C over R squared dB theta, correct? Yeah? Okay. So now I'm going to apply again this fellow, right? So this will be C over R squared dB theta of C over R squared dB theta. So this will be C over R squared. And now I have to do, this is a product, right? So I have to do the product rule, okay? And R is a function of T, okay? So we'll have C over theta, C over, okay, so it will be minus 2 C over R at 3 dr d theta. Okay, what did I do here? Okay, dr. Good, good. Okay, dr d theta times dr d theta, and then plus c over r squared times d to r d theta 2. There you go. Okay, so now this will turn out to be minus 2c squared over r at 5 dr d theta squared plus c squared over r at 4 d to r d theta 2. Okay, so this equation here, the green one, becomes whatever we have instead of our two dots, which is all this stuff. Okay, c squared over r at 4 d to r d theta 2. Okay, minus c squared over r at 3 plus mu over r equals 0. Yeah, that's what it ended up with. And now they say, right, in the exercise, I said, well, now introduce u is 1 over r. Okay, so this means that if we do du d theta, this will be minus, or however you want to do it here. I'll do it the other way around, right? So this means that r is 1 over u. So if we do dr d theta is minus 1 over u squared du d theta. And then d to r d theta 2 is 2 over u at 3 du d theta twice, so it will be a square. And then minus 1 over u squared d to u at d theta 2. And now we substitute, yeah? So here, wherever I see this guy, I'm going to put this guy. And wherever I see this one, I'm going to put all this one. And you know something? You do the job and the miracle happens, okay? So I guarantee it's correct because I did it last night, okay? So you end up with an equation in U that looks like this, okay? Which is lovely. This is called the Binet equation. Okay? And it's a shifted harmonic oscillator, right? So you did it in ODE, how to solve it. So if you solve it, right, and I want to show you something else, okay? So when we solve it, we end up with u of theta to be of the form a cos theta plus b sine theta plus mu over c squared. So this is from standard ODE. But then I said, no, you can actually write this one as a u of theta to be amplitude cos of theta minus or plus theta naught, and then the rest is copied, right? And actually I had a colleague of yours saying, I have no idea how you get this stuff, you know, so A, B is in R. And because you have no idea, and I explained to him, but also, you know, I did it here for you guys. So you see some elementary trick how things are going, and you can write any linear combination of cos and sine as an amplitude times cos, you know, amplitude phase type of thingy. So I can go over it with you, okay? So how do we see in this one what is here, okay? And this used to be done in high school and in first year. For some reason, there is no time to do anything properly anymore, okay? So all right, so in other words, A and B are given. What would be the capital A and the theta naught? So it's a little bit of a trick, okay? First of all, if B is 0, there is nothing to do. If B is 0, then A cos theta will be a capital A cos whatever. So it's the identification is right there. Whereas if b is non-zero, then we can write a cos theta plus b sine theta in this form. And check it out. This is where is the part that I don't know why, you know, nobody's telling you or whatever. There is a trick, you know, any number, any real number can be seen as the tan and cot or cotan of an angle. And this is because tan or cotan, they have their range to be in the entire axis. So any number, right? So if I draw the cotan, right? So it has these asymptotes in minus pi on 2 and pi on 2. And I think the cotan comes something like this. Okay, I'll draw the tan because I remember that one. Okay, so for instance, tan is like this. Okay, tan x. Okay, so any number, I can find an x for which this number will be represented. Okay, if I do cotan, okay, I don't remember how cotan looks like. Okay, you do it for cotan, okay? You do it and see that indeed, no matter what number I'm going to take on the vertical, I will find an angle for which the numbers can be represented as a cotan of that angle. Okay, and once we put it in these terms, b cot, you know, this fellow here, it's written as a cot, but cot is cos over sine. And now I'm using my trig. And here inside is nothing else but cos of theta minus phi. And in front I have this coefficient. So here is my identification. The amplitude is b over sine phi, where phi is that angle for which cot is a over b. And theta naught is minus phi. And if I give you this on the final with no notes, everybody dies. But it's an exercise. It should be done somewhere. It's so fundamental. Because I know, you know, in maths, they tell you, oh, the solution is a cos theta plus b sine theta. And then you go to a physics course or applied maths and you say, oh, no, it's amplitude and phase, right? I mean, there's the representation. And you just stare at it and say, okay, so how'd they get this, man, you know? But it's there, it's there. So let me finish this. You know, I know I'm keeping you longer than usual, but I'll finish this because I wanna have it done. Okay. So this guy was 1 over r, right? So this is 1 over r theta. So now when we flip it, okay, this comes stuff as r of theta is 1 over a cos theta plus theta naught plus mu over c squared, i.e. we can write it as, okay, so I'll put it here. Yeah. Okay, all right. So now if I write it nicely in the form that you'll find it on the web and in any course of satellite motion, huh? No, of celestial mechanics. Okay, where P is c squared over mu and E is a c squared over mu. Okay, all right. And now I ask you also to do some drawings of this. So what you're gonna observe, you're gonna observe that if E is 0, this r of theta is a circle. And actually the radius is really c squared over mu is the value that we found for the circular motion in our discussion in here, right? Of course it has to be, otherwise we're wrong, huh? Okay, so there you go. Whereas for E in between 0 and 1, you're going to discover that r theta is an ellipse. Okay, and we can do a course in an ellipse in conic sections. So it will be something like this, an ellipse with the focal focus in the, where the earth is, right? So there's the focus here. And this is our, oops, let's obey our R of theta, right? So it goes like this, and it goes all around, okay? So actually the motion is in between an R min and an R max, but is a very particular type of motion, isn't it? Because remember how I had the rosette moving around? For the gravitation, that rosette is not moving, it's staying fixed. Okay? Is a very particular case. The gravitation is a very, very particular case of central force. It has so many properties that are just out of the ordinary. Let's just put it like this, you know. So it's quite special, quite special. Okay. And then if we have E equals 1, right, we're gonna discover that R of theta is actually a parabola. Okay, so I won't draw it, but this is something like this, right? And then for E greater than 1, then R of theta is a hyperbola. And actually you can compute, and this is corresponds to the H equals 0, whereas this corresponds for H greater than 0, whereas this stuff corresponds for H in between 0 and HE, okay? Whereas this is H equals HE. And things get one into another. Yeah, okay. All right. So I'll stop here today. Thank you.